Hello, everyone. Welcome to Brain Blitz Audios. In this episode of Mind Maps, we'll be dealing with the fourth chapter in the chemistry syllabus of grade 12 CBSE. The name of this chapter is Chemical Kinetics. And as always, we'll be enlisting the help of a mind map to explain this chapter. Mind maps are pretty effective for last-minute revisions for various exams. However, they can be pretty extensive like this one, and therefore this video is devoted to explaining this mind map and its parts in some detail. So we'll be dividing this mind map into 9 sections, and section number 2 will be divided into a further 5 subsections. So now let's move on to the first section, the general overview of chemical kinetics. So what do we study in chemical kinetics? You know, in chemistry, we study reactions, and therefore we try to understand 3 parts of a reaction. The feasibility of a chemical reaction, which we studied in the chapter thermodynamics in grade 11. The extent to which a reaction will proceed, which can be studied in the chapter equilibrium. And finally, the speed of the reaction. That is the time taken by a reaction to reach equilibrium. So in this chapter, chemical kinetics, we'll be dealing with the speed of the reaction, that is the time taken to achieve equilibrium, which we know as the rate of a chemical reaction. So we'll be learning about the rate of a chemical reaction. We'll be learning about the order and the molecularity of a reaction. Then we'll learn about half-life of a reaction and move on to integrated rate equations and pseudo first order reactions. And then we'll move on to the Irenaeus equation, which is very important, and we'll conclude this chapter with the collision theory. Let's begin. So from chemical kinetics, we're moving on to the rate of a chemical reaction. So how do we define the rate of a chemical reaction? So the rate of a chemical reaction is defined as the change in concentration of reactants or products in unit time. So basically, it is the change in concentration divided by time taken. And we represent this in the unit moles per liter per second or atmosphere per second. So moles refers to number of molecules. Liters is the volume. Seconds is time. And here atmosphere refers to a unit of pressure. And so when the reactions here are in gaseous state, we use atmosphere per second. Otherwise, we use moles per liter per second. And so we find the change in concentration of the reactants or the products, and then we divide it by the time taken to undergo that change. So R is to P is the way reactants to products are represented. So R is reactants and P is for products. And so in a chemical reaction, we usually notice that the reactants decrease in number. Their concentration decreases, while at the same time, the concentration of the products increases. So to find out the rate of a chemical reaction, we can either calculate the disappearance of the reactants or the appearance of products. So we can take the decrease in concentration of the reactants and divide it by time. So that is negative delta R divided by delta T. Delta represents change. So delta R is the change in concentration of reactants. Now, if you notice, both R and P are written in square brackets. The square brackets represent concentration, of whatever quantity is present in between them. So in this case, it's the reactants. So concentration of the reactants is represented as R present in a square bracket. So the decrease in concentration of R will be represented by a minus delta R, because minus represents decrease, delta represents change, and R in a square bracket represents concentration of R, divided by delta T. Again, delta represents change and T is for time. So since the reactants decrease in a chemical reaction, we find out the rate of disappearance or reduction of the concentration of reactants. Now, if we have to express the rate of a chemical reaction in terms of the products, we find out the net increase in the concentration of the products. So it will be plus delta P divided by delta T. Again, P in a square bracket represents concentration of products, and plus indicates that it's increasing. So increase in concentration of P, that is represented by plus delta P, divided by delta T is time taken. So final time minus initial time. That is represented by delta T. So that's how you calculate the rate of any chemical reaction. Either we find out the decrease in the concentration of the reactants per unit time, or the increase in products of a chemical reaction per unit time. So now we move on to some factors which are affecting the rate of a chemical reaction. But before that, let's look at what are average rate and instantaneous rate. So we know that rate is equal to delta is equal to concentration, change in concentration, divided by time taken. However, this can be expressed in two ways: average and instantaneous. So average rate looks at the appearance of products or disappearance of reactants over a long time interval. So we have a reaction running for, say, 10 minutes, and we find that the concentration of the reactants have decreased by a lot, and the concentration of the products has increased by a lot. So what we do is we find out the concentration. So what we do is we average the decrease in the reactants or the increase in the products. So R final minus R initial, so concentration of R final minus concentration of R initial, divided by the total time. So total time T. And again, that's the same for the products. So product final, concentration of product final minus concentration of product initial, divided by time. So this looks at the total reaction that happens in, say, 10 minutes. However, how do I find the rate of a reaction at, say, the 5th or 7th minute of a chemical reaction? So for that, we use instantaneous rate, the rate of change in concentration of a reactant or product at a particular time. So we use differentiation here. So the R average is delta P by delta T. So what we do is we take limits and we extend it to 0. And so that is delta P by delta T. So that makes the time interval very short. And the time interval that is very short is represented as D. So the change in the concentration of the products will now be dP, divided by the change in time will be dt. So this represents a very small time interval. So that is why instantaneous rate is known as the rate of change in concentration at a particular time. And minus represents decrease in the concentration of reactants, and plus represents the increase in the concentration of products. So R instantaneous can be represented as minus d concentration of R divided by dt, or plus concentration of products, that's dP divided by dt. So now let's move on to the factors. So factors which influence the rate of a chemical reaction. What is the rate of a chemical reaction dependent on? So first things first, concentration. So we've known that the rate of a chemical reaction is change in concentration divided by time. So therefore, rate is directly proportional to change in concentration. So when we have a higher concentration of reactants, we will have a faster rate of reaction. So higher the concentration of reactants, faster is the rate of the reaction. What about the influence of temperature on the rate of a reaction? So increase in temperature increases concentration, which increases the rate. So the rate of the reaction increases with increase in temperature. In fact, for every 10 degrees increase, we get twice the rate of the reaction. So the temperature, the rate of the reaction becomes almost double with a 10 degrees rise in temperature. What about if a catalyst is present in the reaction? So a catalyst speeds up the reaction. So therefore, it increases the rate of a chemical reaction. Now, the concept of catalyst will be further explained in the chapter Surface Chemistry. For now, let's know that a catalyst is a substance which does not take part in a chemical reaction, but it increases or speeds up the rate of a chemical reaction. What about surface area? Suppose we have a larger tumbler and a smaller tumbler. The rate of the reaction, R to P, occurs faster in the larger container. So the surface area is really important. So R is directly proportional to surface area. So greater is the surface area, faster is the rate of the reaction. And finally, activation energy. If the activation energy is low, it takes lesser time for the reactants to convert into products. So lower the activation energy, faster is the reaction. So the rate is inversely proportional to activation energy, EA. Now let's move on to the rate constant. So what is the rate constant? Now, suppose we have a chemical reaction, A plus B is C, will be converted to C plus D. So the rate constant is the rate of a reaction when the concentration of each of the reactants remains in unity. So suppose A has a concentration X and B has a concentration Y. So after the chemical reaction, there'll occur a stage where A's concentration is 1 and the concentration of B is also 1. So the rate R here will be represented as K, which is rate constant. Now for a zero order reaction, the rate constant will be moles per liters per second. So we will have 1 mole in 1 liter times 1 second. So that is moles per liter per second. Now in a first order reaction, which is dependent on only one reactant, the unit of the rate constant will be per second, so 1 by second. And in a second order reaction, which is a reaction which is dependent on 2 reactants, the unit of the rate constant will be moles, mole inverse, liter, second inverse. So that will be liters per mole second. So the rate constant is when the rate of a reaction is when the concentration of each of the reactants are in unity. So we find the rate in this situation and we get our rate constant. So rate constant is the rate of a reaction when the concentration reaches unity. The concentration of the reactants reaches unity because the rate of a reaction is dependent on the concentration of the reactants. Now let's look at rate law. So what is rate law? The expression in which the reaction rate is given in terms of molar concentration of reactants, which each term raised to the power which may or may not be same as stoichiometric coefficient of reactants in a balanced chemical equation. So earlier we knew that rate is equal to change in concentration divided by time. Now, in the rate law or the rate expression, we write the rate as rate constant K into the concentration of the reactants, which are raised to some values which may or may not be the stoichiometric coefficient. So sometimes it may be the stoichiometric coefficient. So if it's AA plus BB, then maybe X will be equal to A and maybe Y will be equal to B. But at times for simplification, it may not be A and B, or it may be A by 2, B by 2. So this value can vary. However, the rate law or the rate expression is the expression in which rate is expressed as the rate constant into the concentration of A raised to some value into the concentration of B raised to some value. So the equation here is AA plus BB gives CC plus DD. And our original expression for rate is dr by dt. And so now it can also be represented as rate constant K into concentration of A raised to X into concentration of B raised to Y. Any power. So X and Y can be any power. They may be the coefficients, they may not be the coefficients. So now let's look at the next part, order of a reaction. So the order of a reaction is the sum of the powers of concentration of the reactants in the rate law. So in the rate law, we studied that R is equal to K, A raised to X, B raised to Y. So to find out the order of a reaction, what we do is we just add X and Y. So the value of the sum of X and Y gives us the order of a reaction. Now, in the previous case, we found that the order is 0. So over here, X plus Y is 0. And in a first order reaction, X plus Y is equal to 1. And in a second order reaction, X plus Y is equal to 2. So that is all about the order of a reaction. So when we look at orders of any of reactions, we can have any type of values. It can be 0, it can be 1, it can be 1 by 3, it can be minus 1 by 7, minus 5 by 9. Any value can be present for the order of a reaction. So what it is the sum of the coefficients here, X and Y. So the sum of these powers give us the order of the reaction in question. Now let's look at molecularity of a reaction. So molecularity is the number of reacting species taking part in an elementary reaction colliding to bring out a reaction. So let's say AA plus BB gives CC plus DD. So if you look at the reactant side, we have two species, A and B. So these are our species, different species that are colliding in this reaction. So these are 2 in number. So that makes the molecularity of this reaction 2. Now, molecularity can sometimes be confused with order of a reaction, but one of the main differences is that molecularity will always be positive and it will always be a whole number, say 1, 2, etc. So it always is in the values of 1, 2, 3, etc., and no fractions are present, because these looks at which the number of the reactants that react. So here we have two different species that react. So the molecularity is 2, while the order could be anything which represents A plus B. So the order is the sum of these powers, while the molecularity looks at how many number of different reacting species are present. So that's the difference between molecularity and order. We've studied that the rate equation, so rate can be represented as K A raised to X B raised to Y. Now, and which also is equal to D concentration of R divided by dt. So the change in concentration of the reactants or the products divided by the change in time. So this is the expression of the rate of a reaction. So this expression dr by dt and dp by dt are in differentiated form. So what happens when we integrate these two to remove the differentiation, the d's here? So this is at a particular time period. So when we integrate, we try to stretch it over a broad time period. So the integrated rate equation is the rate equation which is formed by the integration of the differential rate equation. So what we do is we have dr by dt, and we do this. So this is known as integral. So we combine together all the different pieces of values which are differential rate equations to give us a relation between the concentrations at different times and different rate constants. So that is integrated rate equation. So it basically unifies the different points on the graph which give us different rate equations, different differentiated rate equations. So for a zero order reaction where A plus B, X plus Y is equal to 0, that means both of these are 0. So the rate is not depending on the concentration of the reactants or products. So that is known as a zero order reaction. So in a zero order reaction, the integrated rate law is Kt is equal to R naught minus R. K is the rate constant, T is the time taken, R naught is initial concentration, and R is the final concentration. And the graph of this can be represented as R versus T. So this will be the graph for the integrated rate equation of a zero order reaction. And as we've studied earlier, a zero order reaction has the unit moles per liter per second. Similarly, let's look for the first order reaction. Over here, the rate will be equal to K times concentration of A times concentration of B. Because both of these, the X plus Y here, that is the order, is equal to 1. So it's dependent on at least one of the reactants. So in this case, KT is equal to ln R naught divided by R. So let's write this equation as KT is equal to ln R naught minus R. So let's look at the quantities here. K is the rate constant, T is the time taken, and ln is known as natural logarithm. So this is a mathematical operator which is formed when we integrate the inverse of the concentration. So when we do this, we get ln R, so natural logarithm of R. So in this case, R naught minus R, which is taken under a natural logarithm, will lead to division of the two. So KT is equal to ln R naught divided by R, concentration of R, the naught divided by concentration R. This is initial and this is final. And so over here, the graph will depend on ln R, that is the natural logarithm of the concentration of the reactants, versus the time taken, like this. And the unit of a first order reaction is given as per second. Now let's move on to half-life of a reaction. So half-life will deal with half of the concentration of the reactants. So the half-life is the time taken in which the concentration of a reactant is reduced to 1/2 of the initial concentration. So suppose we have a reaction with its concentration R naught. So it's changed to R in time in half of the time. So what it means is that R, the concentration of R, is equal to R naught divided by 2. And so according to our equation of the rate constant, it will be concentration of R divided by T. So at time T by 2, we get the rate constant as half of the initial concentration divided by T half, which is the half-life. And so on playing with the reaction, we get T half, which is the half-life, equal to R naught by 2 into K. So that'll be R naught divided by 2K. So this is the equation for a half-life of a reaction. So half-life of a reaction is R naught divided by 2K. For a zero-order reaction, it is the same thing. But for a first-order reaction, the addition of a natural logarithm in the calculations leads to the half-life being independent of the concentration of the reactant. So T half in a first-order reaction changes to 0.693 divided by the rate constant. Now we'll look at a special type of reactions known as pseudo first-order reactions. So most of the time, we can calculate the order of a reaction using this formula. K is equal to A raised to X, B raised to Y, and the order will be equal to X plus Y. However, in some situations, the concentration of some of the reactants, so some reactants, say A has a normal concentration, but B has very high concentration. So therefore, there is no net change. So then K will be dependent on A, so it will be in a different order. So that is known as pseudo first order reaction. So we have a reaction of, say, second or third order, but under certain conditions, it behaves as a first order reaction. So one of the best examples is the acid hydrolysis of ethyl acetate. So ethyl acetate plus H2O are our reactants. So in hydrolysis, we find that the concentration of H2O is very high. So that means there is no net change. And so since there is no net change, the rate constant will depend only on the concentration of ethyl acetate. So although this is a second order reaction, one that should depend on both the concentration of ethyl acetate and water, it only depends on the concentration of ethyl acetate. So that makes this act as a first order reaction when it is not a first order reaction. So these kind of reactions are known as pseudo first order reactions. Another example is the inversion of sugar from sugarcane. So this will be cane sugar, that is C12H22O11. And so we do inversion on this sugar to get glucose and fructose. So this reaction is also a pseudo first order reaction. So it has a different order, but it acts as a first order reaction. Now let's look at one of the most important parts of this chapter, the Irenaeus equation. So when particles of the reactant collide to form products, we use the Irenaeus equation to calculate the rate of the reaction. So the formula for this is K is equal to A e raised to minus EA divided by RT. So K is the rate constant. A is referred to as the frequency factor. So what this means is the frequency of collisions of the reactants. So a chemical reaction is thought of as the collision between reacting species, say A and B. So when they collide, they give us new products, say C. So that is the way in which we imagine chemical reactions. So the frequency in which A and B collide is referred to as the frequency of collisions, and that is measured by a frequency factor A. And that is the A represented in the Irenaeus equation. What about E? Now, E is Euler's number. And so this is a mathematical quantity, which is approximately equal to 2.71, blah, blah, blah. And that number is also endless. Now, EA, this is referred to as activation energy. So this is the minimum energy required to convert reactants to products. So the minimum energy in which a reactant must be heated in order to at least receive an unstable intermediary or the product is known as activation energy. So reactions must have a certain amount of energy to convert the reactions into products, and that energy is known as the activation energy. R represents universal gas constant. So this is 8.314 times 10 raised to 6. And T represents the temperature and in which the reaction takes place. So the activation energy is the energy required to form an intermediate known as the activated complex. So suppose we have a reactant trying to convert into a product, we will reach a stage where it is Rp. And this is unstable, so it then dissociates to form the product. And so the energy required to reach this stage is known as the activation energy. And so it's a minimum energy. So what we do is we find the threshold energy of a reaction, and we subtract the average kinetic energy of the reacting molecules. Since these molecules are moving, we need to find out their average kinetic energy using the Maxwell distribution curve. So it finds out the maximum number of molecules undergo which kinetic energy, and they use that as the average kinetic energy. And the threshold energy is the energy at which the reactants start converting into this activated complex. So this is all in all about the Arrhenius equation. Now we move on to the final part, which is the collision theory. So over here, the rate of the reaction depends on the collision frequency and effective collisions. So earlier we've understood that when these reactants collide with each other, they form products. So that is the theory, collision theory. And so over here, the rate is dependent on the frequency, and it is also dependent on effective collisions. So what is frequency here? Frequency is the number of collisions per unit volume. So suppose we have a volume V, and we have the suppose number of molecules N. So N by V would give us the frequency of the collision frequency of this reaction. And so that is represented by ZAB. How do we represent the rate of a reaction using collision theory? So the rate is equal to PZAB e raised to minus EA by RT. Note that the ZAB mentioned here is same as the A mentioned in the Arrhenius equation. So over here, ZAB represents the frequency, EA represents activation energy, R represents universal gas constant, T represents temperature of the reaction, and the P represents the steric or probability factor. So the reason why we calculate this is that in collision theory, the proper orientation of the molecules is needed for an effective collision. So suppose, say, A and B are in the correct orientations, they form C. But suppose A is like this and B is like this, then the collision is not perfect. And so when the collision is not perfect, no product formed. So effective collision is the collision in which the molecules collide with sufficient kinetic energy and proper orientation for breaking of bonds and formation of new bonds. And so to find out the effective collision in a chemical reaction, we use the steric or probability factor that represents the orientation that a molecule A is in. So that is represented as P. So we multiply P to the rate of a chemical reaction, which is ZAB, the frequency, times the Euler's number E raised to negative of activation energy divided by the universal gas constant into temperature. So that is the rate of a chemical reaction in terms of the collision theory. So that concludes the chapter chemical kinetics. So over here, we focused on the rate of a chemical reaction, the ways in which we can represent the rate of a chemical reaction. On the way, we studied quantities such as order and molecularity of a reaction. We learned about the rate constant, which is the concentration of the reactants in unit. So it's the phase, the rate of the reaction is equal to moles per liters per second. So that is where the concentration is 1 and time is 1. So over here, the rate of the reaction will be equal to the rate constant. So we found out the rate constant, and we used the rate constant to find out the integrated rate equations for a zero order and a first order reaction. We then moved on to the collision theory and Arrhenius equation. So this is another way of representing the rate of a chemical reaction. So in Arrhenius equation, we found out the rate constant using the frequency of the collisions of the reactants A and B. And in collision theory, we found out the actual rate of a reaction using the frequency and the steric factor, which determines whether an effective collision has taken place or not. And so we use that to find the rate of a chemical reaction. So that's all about the chapter Chemical Kinetics. We hope that you enjoyed this video. For more of our useful content, please subscribe to our channel. So we'll be back with more videos on mind maps, NEET preparation, and other useful and interesting content. Until then, stay tuned. Ta-ta for now.